What's up, guys? This is Dr. Vivek Palipuram bringing you the lecturette number 3 for ECPE 127 random signals. Now, in this lecturette, I'm going to discuss the properties of the CDF of a continuous random variable and solve some probability problems using the CDF of a continuous random variable. Now, the CDF, the cumulative distribution function, is actually a complete probability model of any given random variable. What it means is that you can solve probability problems and obtain probabilities of different events for that given random variable. So let's recap the properties of CDF. We have already seen the properties of CDF for discrete random variables. They're still very much applicable for even the continuous random variables. For example, the CDF at negative infinity is equal to 0. The CDF at infinity is equal to 1. The reason being, probability that x is less than or equal to negative infinity is 0 because there's no number that is less than or equal to negative infinity. Probability that x is less than or equal to infinity is 1 because all numbers are always less than or equal to infinity. Now, if you have to find the probability that x belongs to an interval, you can use the CDF. So specifically what you do here is subtract the value of the CDF at the endpoints of the interval. So for example, if I would like to find the probability that x is greater than or equal to x1 but less than or equal to x2, I perform the CDF of x2 minus CDF of x1. Now remember, you guys, with continuous random variables, we will always be interested in solving problems that take this form. We will always be interested in finding the probabilities that a given continuous random variable belongs to a particular interval. This is the only type of problem that we are going to solve with them, because the probability that random variable x takes on a specific value small x is 0 for continuous random variables. Recall the example of the spin the pointer problem. The probability that your pointer stops at a very specific angle is actually equal to 0. So remember, we will always solve problems like this. So all of our problems are going to take this form. So that brings me to problem 19.2. So the cumulative distribution function of the continuous random variable y is 0 for y less than 0. It's equal to y over 4 for y between 0 to 4, and it is equal to 1 for y greater than 4. So what we need to do first is sketch the CDF and answer some probability questions. Now what my recommendation is to you guys, and that is to stop or pause the video right here and to try to solve the problem on your own. And once you're done, you can unpause it. So next, I'll solve the problem 19.2. So first, we need to plot the CDF. So the CDF of y will take a form that looks something like this. So on the x-axis, you have the variable y, and on the y-axis, you have f of y. Now, the CDF is 0 for y less than 0, and between 0 to 4, this assumes a straight line. Specifically, it's a straight line y over 4, and then after 4, this is a constant at 1. So that's the sketch of the CDF of y. Now to find the probability that y is less than or equal to negative 1, just find the value of the CDF at negative 1. Negative 1 is right here where the CDF is equal to 0. So the probability that y is less than or equal to negative 1 is 0. To find the probability that y is less than or equal to 1, calculate the value of the CDF at 1. So 1 is right here. So the value of CDF at 1 is equal to 1 over 4. And that can be obtained by plugging the value of y equal to 1, giving you 1 over 4. To find the probability that y is greater than 2 but less than or equal to 3, you need to subtract the CDF values at the endpoints like this: f of y at 3 and f of y at 2. And this can be obtained like this. Substitute for y as 3 minus substituting y as 2, giving you 3/4 minus 1/2, giving you 1/4. So that's the probability that y is greater than 2 but less than or equal to 3. Now this brings me to a very important point right here. When you talk about probabilities for continuous random variables being in an interval, whether the endpoints are inclusive or not does not matter. Meaning that right here, we are talking about y belonging to 2 exclusive but 3 inclusive. We are interested in that probability. For continuous random variables, the endpoints of the intervals, they do not matter, which means that probability that y is 2 exclusive and 3 inclusive is actually equal to probability that y is inside 2 inclusive, 3 inclusive, which in turn is equal to probability that y is in 2 inclusive, 3 exclusive, which is equal to probability that y is 2 exclusive and inside 3 exclusive. So all of these equations lead to the same probability answer. The reason why the endpoints do not matter is because probability that your random variable y is equal to these endpoints is actually 0 for continuous random variables, and therefore it does not matter whether your endpoints are considered as inclusive or exclusive. So remember that fact. The next problem that I have to solve here is probability that y is greater than or equal to 1.5. So to find the probability that y is greater than or equal to 1.5, I can just solve for 1 minus probability that y is strictly less than 1.5. Now, because it doesn't matter whether y is strictly less than 1.5 or not, because the probability that y is equal to 1.5 is 0, I can still write probability that y is less than 5 as probability that y is less than or equal to 1.5, which is equal to 1 minus f of y at 1.5. And when I plug in the value for y as 1.5 in this equation, I get 1 minus 3 over 8, which is equal to 5 over 8. So that's the probability for y is greater than or equal to 1.5. What about this? What is the probability that y is equal to 3? Always remember, the probability that your continuous random variable is going to take on a specific value is always equal to 0. Moving on to the next problem. So pause your video here and solve problem 19.3 first, and then I'm going to give you the solution. Okay, so let me give you the solution for this problem. And here what I'll do is I'll solve for C, I'll solve for this, and I'll solve for that. Or you know what, I'll just solve for C, and I will solve for the C part. So either way, I'm just going to focus on C. And the remainder, I would like for you guys to solve on your own. So let's solve for problem C. Now, let's solve for C, part A. So here, I need to find the value of the variable C. It's not a variable, it's a constant C for the CDF. Now, to find the value of constant C, I'm going to use the fact that your CDF for a continuous random variable is always going to be continuous. So f of y is going to be, or f of v in this case, is going to be continuous even at those places that seemingly look discontinuous. So if I were to plot f of v here, the plot is going to look something like this. It is 0 for v less than -5, then between -5 to 7, it's taking some sort of a parabolic shape, and after 7, it's equal to 1. Now, this point right here, 7, appears to be a point of discontinuity, but there is no discontinuity in the shape of a CDF of a continuous random variable. So if I were to take the value of the CDF at a point that is slightly less than 7, let's call it 7 minus, that will be equal to C at v plus 5 squared at v is equal to less than 7. And if I were to consider a point that is slightly above 7, let's call it 7 plus, f of y at 7 plus is equal to 1. Now, because it's a continuous CDF, both of these values will approximately be equal to each other, meaning that f of y at 7 minus is equal to f of y at 7 plus, because it's a continuous CDF. Since CDF is continuous. So to find that value, I can evaluate the limits. So c times v plus 5 whole squared at v is equal to 7 is equal to 1. And when I solve for v, when I solve for c, I get 1 over 144. So that's the value of c, using the property that CDF is always continuous. And whenever you have such problems having to find the values of a constant, use this property of the CDF. Now let me solve problems part C, where I need to find the probability that the absolute value of v is less than or equal to 2. If you were to consider the number line, here I have -2 to 2, all the points that are in this interval are going to satisfy this condition. For example, if I were to take -1, modulus of -1 is 1, which is in fact less than or equal to 2. All the points that are outside are not going to satisfy this condition. For example, if I were to take a point 3 here outside of this interval, 3, the absolute value of 3 is 3, which is not less than or equal to 2. In fact, it is strictly greater than 2. So the probability that modulus or the absolute value of v is less than or equal to 2 boils down to finding the probability that v is greater than or equal to -2 but less than or equal to 2. As again, the endpoints, whether they are included or not, doesn't matter. So to find this, I just can apply the CDF and subtract the values of CDF at the endpoints of the interval. So f of I at 2 minus f of I at -2. Which gives me 1 over 144, 2 plus 5 squared minus -2 plus 5 squared, giving me 40 over 144. So that's the probability of part C. What I would like for you guys to do is solve part B and part D on your own. So that brings me to the end of lecturette number 3, where I showed you the properties of a CDF of a continuous random variable, and we solved some probability problems using the CDF. Now, the good news is, well, it's totally up to you whether you consider it as a good news or not. The good news is that we will not be relying on CDF anymore to calculate the probabilities of continuous random variables. Instead, we are going to use the derivative of a CDF, which is called probability density function, to calculate the probabilities of random variable. At the end of this lecturette, here's what I would like for you guys to do. For our class on Monday, 22nd March, by 2 p.m., I would like for you to submit this in-class participation problem. So this is the CDF of a random variable, x. What you need to do is find the probability that x is in the interval 2 to 4 inclusive. In my next lecturette, I'll discuss probability density function, which is the most commonly used function to calculate probabilities for different events for a given random variable. We are going to discuss the expected value of a continuous random variable, and we will also refine our differentiation and integration skills. Now, for Wednesday's in-class participation, here's what I would like for you guys to do. For Wednesday, 24th March, by 2 p.m. on Canvas, you will upload your pencil and paper work for the following problems. So just solve some of these problems that I'm going to give you next using pencil and paper. Take a nice picture of it and just upload it on Canvas. And here's what you're going to do. So let f of x be equal to a function x squared plus 2x plus 1. All right. Let g of x be equal to e to the negative 3x. Define h of x as f of x times g of x. Here's what you're going to solve for. You'll first give me d by dx of f of x. So differentiate f of x with respect to x, d by dx of g of x, and also give me d by dx of h of x. Give me an indefinite integral of f of x dx. Give me a definite integral of g of x dx, and the limits are from 0 to 3. And also give me a definite integral of h of x dx, and the limits are from 3 to infinity. So these are the 6 problems that you will have to solve for Wednesday, 24th March's in-class participation problem. For Monday's class, you are going to give me the solution for this question right here. All right, guys, so this brings us to the end of lecturette number 3. In our next lecturette number 4, I'm going to introduce you to probability density functions, which are the most commonly used probability models to solve probability problems for continuous random variables. Adios.